Okay, so this is the second video that you should be watching, and I'm just going to walk you through how to analyze your data for the lab so that you can come up with a straight line equation and be able to answer some of the analysis questions. So hopefully you were able to come up with a graph of pressure versus volume, and for this graph I was asking you to put pressure in newtons per meter squared, and volume had to be in either milliliters or cubic centimeters, and those are basically the same thing. Okay, and you probably have data that maybe didn't go anywhere for a little bit, but then sort of went down. Okay, now if you have a lot of points like this that are more than 2 or 3, you might want to get rid of the first 2. And that, of course, is where friction is keeping the piston from moving downwards. Because we just want to focus on this behavior, which is where basically V is equal to a constant over P, or P is equal to a constant over V. And you might remember that earlier in the year, what we did to linearize was we did stuff to the X variable, and this time we did something to the Y variable. We're going to do 1 over volume, and the units for this, which we'll talk about in a moment, will be 1 over meters cubed, and we'll have the same units for pressure. Now the reason that I'm choosing to do it this way, to change the Y values, will become clear a little bit later on. We'll find out that we actually forgot something that when we add it back in would affect our data. Okay, so just a reminder that the volume in milliliters or centimeters cubed is just strictly what you have measured off of the syringe, and it's going to have uncertainties like this that are the delta V's. So maybe it's plus or minus 0.5 milliliters, which are small, but they can show up. Now pressure on your x-axis will be the actual x value, but you may have calculated delta P over P as a percentage. So maybe it's 0.08, for example, and the pre-flight it was 0.18. But that's a percentage, 8% or 18%. And that's 8 or 18% of the pressure itself. So the error bar that we want to draw here is actually delta P, which is going to be P times whatever the percentage is. So let's say your pressure is 10,000 and your error was 8%, then you would have 10,000 newtons per meter squared times 8%, and that's going to be 800 newtons per meter squared. So that means that this would actually have a size of 800. Okay, now while I'm on this topic, I should remind you that these pressures should be into the tens of thousands, and the biggest pressure that you should have should be somewhere around, depending on how much mass you used, somewhere in the range of 100,000. Okay, and remember that the pressure is force over area. So if you're dividing by 4.9 centimeters squared, that's not good enough because you need it in meters. So 4.9 times 10 to the minus 4th meters squared. How do we get that? Well, you have to multiply by 1 meter over 100 centimeters and then square that. Okay, and then force is mg, like we talked about previously. Okay, so that's what your first graph is going to look like, and the handout that I gave you for the lab states that you need to put both uncertainties for this first graph. Now the second graph, you need to do uncertainties only for pressure. We haven't really learned how to do uncertainty for 1 over volume, and it's actually a calculus thing. So we're not going to worry about that right now. But if you're interested, you could try looking it up, and if you figure it out, maybe some extra credit. Okay, now this second graph, I'm going to actually draw the axis right here, because the second graph doesn't go through 0 like we hope. It actually goes more like this, and there's an intercept here. Okay, and I'm going to use some of the numbers that another group had earlier. And so one of the equations that people had earlier was, whoops, sorry about that, 1 over volume equals 0.140 times pressure plus 15,200. And we'll talk about the units in just a second. But on your second graph, if you're not seeing numbers that are in this ballpark, so in other words, your intercept should be somewhere between 10 and 20,000, preferably like 18,000 or so. It just depends on your setup, by the way. And if your slope is not a decimal that's somewhere between about 0.1 and 0.3, then you're doing something wrong with your units. And let's just talk about a few things to check. First of all, the pressures, as I noted, should be going up by about 10,000 each time. And the reason for this is, let's say that you have 0.5 kilograms for your first point, and let's say that you measure the radius is 1.3 centimeters. So then your pressure would be mg over pi r squared, and so mg would be 0.5 times 9.8, which is 4.9 newtons, and then this is going to be pi times 0.013 meters squared. This is the other way to do it, is to convert from centimeters to meters and then square it. So by the way, if this is all right for you and you want to fast forward a little bit, that's totally fine. So 4.9 divided by pi times 0.013 squared is going to give me 9,230 newtons per meter squared, and that's just for my first point, and all the others will be multiples of that. So like I said, you're going to get up to about 90 or 100,000. Now the other thing to look at is your 1 over volume. Okay, these should also be in the tens of thousands. So why is that? That doesn't make any sense. Well, if you think about it, we're doing 1 over volume, but the units are 1 over meters cubed. So you start with the volume such as 50 milliliters, which is 50 centimeters cubed. But if we want to convert that into meters cubed, we have to do the same trick as up here, but instead of doing it squared, because we have centimeters squared, we have to do 100 centimeters cubed. Everything has to be cubed. So basically what you do is you take the exponent here and you just distribute to everything. So there was a 3 here that I then distributed. So 100 cubed is 1 million, and if I was in class, I'd be doing the Austin Powers thing. So 50 divided by 100 cubed is 5 times 10 to the negative 5th meters cubed, but that's V. Therefore, if I want to get 1 over volume, I have to do 1 over that. And that's where I get my extremely large numbers from, because that's 20,000 1 over meters cubed. Okay, so once you've done that and checked and made sure that your graph is correct, then let's move on and talk about what everything means. Okay, so we just talked about the intercept, and the intercept is 1 over meters cubed. And what about the slope? Well, the slope is going to be 1 over meters cubed and then newtons per meter squared. So let me just bring that down here. Okay? So the slope would be 1 over meters cubed. Let's write it like this. Divided by newtons per meter squared. So you have to flip it. That's 1 over newtons times meters. Okay, so that means that the slope of our graph, so 1 over v is equal to 0.140, 1 over Newton meters times pressure plus 15,200, 1 over meters cubed. So there's a couple of things to take away from this, okay? First of all, the unit of the slope is 1 over Newton meters, which is force times distance, which is work, so it's in joules. Now the reason for this is that as the plunger is moving downwards, there's a force being exerted on it, and it's moving a certain distance. So that's where this is coming from, that really work is being done on the gas. Okay, the gas inside the cylinder. So that's an important thing to take away from these units. Okay, so now we're going to start talking about how to answer some of the analysis questions in the lab. And the first one is, why doesn't it go through 0? Okay, so if you think about this, if this is 1 over v and this is p, then in a perfect world, it would be going through 0 like this. Okay, in other words, if 1 over volume was equal to 0, pressure would be equal to 0. Now 1 over volume basically means that volume itself is infinite. And so let's just think about this and see if this makes sense. If you had an infinite volume, so you start with whatever's in your cylinder and then you let it expand to an infinite volume, the pressure is going to be basically 0. So this makes sense. And so what we expect to happen was this dotted line. And so what this means is that we're actually off by this amount right here. Now the reason that we're off is that we forgot the fact that we're alive, we're breathing air, and there's air in the classroom. That air exerts air pressure of 1 atmosphere, which is the same thing as 101.3 kPa. So that means that in our data table, when we had pressure and volume, when we wrote 0 for the first point, that wasn't true. It was actually 101,300. Okay, when we wrote 9,230, that's not true. It was 110,000. But we didn't do that, and we're not going to go back and fix this. What we are going to do is to use our equation to determine the air pressure in the room. And to do this, we're going to basically solve for P when 1 over V is equal to 0. So we're solving for the location of this point right here, and then how much we're off, absolute value of that will be the air pressure in the room. And so hopefully we're going to get something that is a reasonable answer. Okay, so let's plug this in. 1 over V will be 0. Then we have 0.140, 1 over Newton meters, times pressure, plus 15,200, 1 over meters cubed. We solve that for pressure, and that's the pressure of the air. And we set absolute value, right? So it's negative 15,200, 1 over meters cubed, and that's divided by 0.140, 1 over Newton meters. Okay, now if you do the math on this, you're going to get that this is about 109,000 newtons per meter squared, which is like 109 kPa. Maybe it's 110 or 111, but it's close to that. And so the point is that we are close to 101.3. Okay? And this is also why we couldn't do 1 over P, because all of the P values were 100,000 less than what they were supposed to be. So 1 over P would be way, way, way bigger than what it's supposed to be. And you actually get a curve when you do that, not a straight line. Okay, so that's why we didn't do that. I'll just forget we ever saw that. Okay, that's the first thing. This is how we find the air pressure in the room. Now, the slope itself is going to tell us a couple of things. Okay, first of all, we talked about work already, but remember that going back to our graph, if this is 1 over v and this is, and this is pressure, then the variables that make up the slope is actually 1 over v divided by p, which is 1 over piv. I say piv, you say, that's right, nert. So it's 1 over nert. So that means that the slope of our graph represents 1 over nRT. Okay? And that means that we can immediately solve for the number of moles of gas that we had by doing 1 over slope times RT. Okay, so 1 over sloper. I'm making that up. Okay, so if we use that the slope here is 0.140, 1 over Newton meters, then we do it kind of like this. Okay, so 0.140, 1 over Newton meters. We'll put R there in a second. Let me move this over. We'll put R in a second. And then T, let's just say 294 Kelvin. I think that's the number that I used. Okay, now R, you're used to R using 8.31. I want to say, is it kilopascals times liters over mole Kelvin? Well, it turns out that kilopascals times liters is the same thing as joules. And that's because there's basically 1,000 meters, wait, I'm going to get this right. There's 1,000 liters in 1 meter cubed, but there's 1,000 pascals in a kilopascal, so the thousands cancel out. So we're going to use 8.31 joules per mole Kelvin. Kelvins will cancel, Newton meters will cancel, and N is going to be basically 1 over 0.140 times 8.31 times 294. So 0.14 times 8.31 times 294, and take the inverse of that, and we're going to get N is 0.0029, and then it's 1 over moles, and sorry, this just disappeared. So it's 1 over moles, which flips and becomes moles. So now we know the number of moles in the sample, in the cylinder. But wait, there's more. In chemistry, you learned that for an ideal gas, that 1 mole of an ideal gas takes up 22.4 liters of volume. So what we can do is we can work backwards from the number of moles and say that if 1 mole is 22.4 liters, then I can predict that this group that I've used the numbers for had a starting volume of, well, let's see, this is 0.0655 liters, and that's about 66 milliliters. Now, I actually had this class earlier today, and they told me that they actually started with 60 milliliters. So being off by 10% doing all these calculations is pretty good. Okay, so let's just recap what I went over in this video. We talked about how to make the graph of 1 over volume. We talked about how to find the equation. We talked about why it doesn't go through 0 and what this means, the air pressure in the room. And then we also talked about the meaning of the slope, that the slope can be used to find the number of moles of gas, and it can also be used to find the starting volume. Okay, so I know this was a little long, but we're basically going to spend this much time in class with me going over this anyways. So 6 of one, half dozen of the other. So what you're going to do for the remaining time in class today is you're going to work with your partners on your lab report. And if you finish this video faster than your lab partners, that's okay. Figure out what you're going to work on and do that quietly. And when they finish, then you can meet up with them. Okay, so I do expect to be back in school on Thursday, and I'll see you then, or Friday.